Okay, we're going to continue looking at Newtonian mechanics, and we're going to start taking a look at the sort of the first of the forces that we had kind of passed by in the intro courses, saying that we need to develop some techniques. So we're going to start by taking a look at velocity-dependent forces. Pardon me there. Okay, so taking a look at velocity-dependent forces here. Um, and it turns out that in general, most of the problems of this type have to be solved by numeric techniques. And depending how good of a job you want to do, those numeric techniques could get quite hairy. For instance, with air resistance, really the best way to model it is to do computational fluid dynamics and try to model as many molecules interacting with the object as possible. This is what, say, the major automotive manufacturers do when they're working on designing their cars, and they have very, very large computers indeed to make that happen. Um, Other classes of problems you don't have to be quite so um, fussy about when you're working on, but even so, they can get a little tricky. And there's one, so when you're looking at doing things numerically, you have to remember there's one very big rule. GIGO, GIGO. That stands for garbage in, garbage out. GIGO. There we go. So this means that, if you make some small error in your code, you'll typically end up introducing some kind of fictitious force or something like that. In any event, your code is going to give you an answer that's pretty much totally bogus. So even though we're probably at a point now in many, many areas of physics where most of the problems that we have to tackle have to be tackled numerically, there is still plenty of room for analytic technique, because if nothing else, just to validate our code, we need to look at what I call the toy models, things that we know how to analyze analytically, and then we configure our code to match those toy conditions and see if they give us answers that match what we can calculate for ourselves. Well, it's not a 100% guarantee that your code is right. It definitely takes you a very, very long way. So we're going to start here by saying, well, let's imagine that we could write our code, write our force, sorry, as some constant force plus some part of the force that depends on the velocity. Okay, then by Newton's second law, that will give us mass times the acceleration, which we'll write as dv dt. That is going to equal our f naught plus f of v. And if you remember, there's a little trick we did before with this dv dt business. We can use the chain rule to turn it into dv dx, dx dt, and then we realize our dx dt is v. So we can write this as mv dv dt equals our f naught plus f of v. Okay. Now, what we're going to be looking to apply this to in this video is fluid resistance. Yeah, don't forget that air is a fluid, but we can be more general. So fluid resistance. In general, this is where you've really got to get the computers out and do the computational fluid dynamics, and it's ugly. And then you need to validate the computational fluid dynamics experimentally. That's why engineers are always busy running things in wind tunnels or wave tanks or whatever. But a lot of times if you're trying to get a good rough and ready answer and you don't have some totally bizarre airfoil, you can usually model the drag force as by doing a series expansion. We're just kind of cheating here. And since we're cheating here, it's only really worth keeping the first two terms. If we have to worry about cubic contributions, then, we're probably going to have to work a little harder at it. So we have the minus sign here because whichever way the velocity is, if it's going to the right, we need the force to point to the left, or if the velocity is going to the left, we need the force to go to the right. So that minus v is getting us the correct direction. So then we'll have some coefficient of drag C1 for the linear term, and then we'll have a C2. Now for the quadratic, we've got to be super careful. The reason that I've been writing it like this, already pulling out the 1 minus v, is if I just willy-nilly wrote plus C2v squared, that drag force would end up always pointing up or to the right, which may or may not be what we need. So we actually have to multiply this by the absolute value of v. I'm sorry, but that's just what we have to do. And it often means that when we're solving these signs, we may have to first look at, say, motion to the right, solve for it, motion to the left, solve for it, and then join boundary conditions. Okay. Now, that's the general case, and hopefully you don't actually have to mess with the general case. Because it's really, really ugly to solve. But here again, since we've already made an approximation by just treating this as a series expansion, only keeping the first two terms, we can take a look at a couple of limiting cases, and that covers a lot of our situation. For instance, if v is small, we can go away with approximating our drag force as just minus C1v, and we'll be all happy about that. By the same token, if our velocity is large, the linear term won't contribute much compared to the quadratic term, and so then we can get away with approximating it as, now here we got to be careful, plus or minus C2v squared, and we choose the sign that opposes the motion. Oops. Wow, that was novel. Okay. And if we suspect that it might reverse motion for some reason, then again, that's a case where we'll have to treat it first in the one regime, then the other, and then match boundary conditions. But for now, for this video, let's just go and take a look at the linear case and see what we can get from it. And we can start with horizontal motion. And we'll assume it's all frictionless and everything. That way we can take gravity out of the picture. So, got some object that's moving to the right like so. It'll be feeling our drag force. Pointing against it. Okay. In that case, our Newton's second law will become, well, the force is minus C1V, and then we have plus M dV dt, and we'll just make a little note of that, call that star. This solves pretty straightforwardly. We can rewrite this as dt equals minus m over c1, and then we'll have a dv over v. And then go ahead and integrate both sides. We can integrate this from 0 to t. We can integrate that from v0 to v. And so we get t equals minus m over c1 times the natural log of v over v0. Now, that is a solution. Usually we're more interested in the motion variables, so we got to get the velocity disentangled out from that. So we'll have to take some antilogs to make that happen. And when we do, we will get v equals v0 times e to the minus c1t over m. Okay, now if we want to get the position as a function of time, we can go ahead and realize that v is dx dt. And so we can go ahead and say dx equals v0 e to the minus c1 t over m dt. We'll integrate that from 0 to x. We can just assume we started at the origin. And we can integrate this from 0 to t. So we get x equals, we can get x equals, and then we go ahead and integrate this. This is going to bring down a minus m over c1. So we get a minus mv0 over c1, and then we will have e to the minus c1, e to the minus c1t over m minus e to the minus c1 times 0 over m. Well, that becomes 1. So now, just to clean this up a little bit, I've got a minus here, and then I have a minus 1 there. Probably best to just go ahead and distribute the minus signs through. So that will become m v0 over c1 times 1 minus e to the minus c1 t over m. Woot. All right, so how do we go ahead and interpret this? My thought here is to just start by going with time 0 and then seeing what happens as we approach time infinity. At time 0, this exponential is a 1, so we get 1 minus 1 is 0, and that just says we started at x equals 0. If we wanted to, we could have had an x0 in there, not a big deal. Now what if we go to time infinity? At time infinity, we'll have e to the negative infinity, which is equal to 0, which means that our position is going to asymptotically approach mv naught over c1. So what we get is that the object is slowing down. That makes sense. And at the end of all the motion, it will end up over here. Okay, let's see how the velocity behaves as a function of time. Now there are two ways that we can go about doing that. So let's go and do sort of the direct gutted out approach. We can, well, actually, let's not do that just yet. Let's instead go ahead and use our little trick again. We can write dv dx is equal to dv dt times dt dx. We can look at that and go, hey, that is dt dx would be 1 over v times dv dt. All right, so if we go way back, if we remember where we started from, right here, the minus c1v business right there, we can go ahead and rewrite that. Remember, dv dt is equal to v dv dx. So from star, this will give me v dv dx, which is equal to dv dt, will be equal to minus c1 over m times v from what we had before. Okay. So I can cancel v's here and here. Sorry, this should be reading v dv dx right there. So this gives me dv dx equals minus c1 over m. So I can rewrite that as dv equals minus c1 over m dx. Integrate from v naught to v, integrate from 0 to x, and I get that v equals v naught minus c1 over m times x. So what we get here is that as we go with displacement, the velocity decreases linearly. It's kind of an interesting result. So let's go ahead and, just for the grins, do this a second way. Just do it by the less elegant gutted out approach. So we already found that v equals v naught e to the minus c1 t over m. And we also already found from before, so I'm just recycling results here, that x equals mv naught over c1 times 1 minus e to the minus c1 t over m. Oh, if I go take a look right here, I have that same exponential in both. So I can make this much more tractable by solving for that exponential. So this will give me that the exponential is equal to v over v naught, and then I will just go ahead and stick that in over there. All right, so that gives me x equals mv naught over c1 times 1 minus v over v naught. All right, so I can rearrange a little bit. C1 over mx equals, Now if I distribute that v naught through, I get a v naught minus v, and then I can rearrange for the v and get v equals v naught minus c1 over m times x as before. So the big point of this here is sometimes get in the habit of looking at these exponentials here and other exponentials, trig functions, whatever that show up. Every so often you can look at them and kind of think of them as the variable you want to get rid of. This way we didn't have to integrate anything with respect to time and make the time dependence go away or anything like that. All right, so that was the first case there. Now let's actually have it fall, so this will be vertical motion. So there's my object. We'll have it falling down to begin with anyway. So if I go ahead and look at the forces I've got gravity pulling down, and I have my air resistance pushing up. But we got to be careful here. This is still just going to be minus C1V, because remember my V here is negative, and so minus and minus is a plus, so I've already baked it into the cake. I don't need to change any signs. But anyway, with that, our Newton's second law will become minus mg minus C1V equals m dv dt. All right, so we can go back to the same well we went to before. You can get the dt on the one side and everything else on the other side, minus m dv over mg plus c1v, like so. Now you might look at that and go, ooh, that's ugly. And certainly at this point, if I was feeling lazy, I would go ahead and just type it into Mathematica and integrate it. That might be instructive just to remind you of some of your calculus. And remember that we can do this by a u substitution. So let's do a u substitution on this, shall we? We'll let u equal the thing that we don't like too much, mg plus c1v. So then du becomes c1 dv. Yay. So dv equals du over c1. Woot. Okay, so I can go and stick that in there. And so with our u substitution, we now have dt equals minus m over c1 du over u. And that sure looks like something I understand how to integrate. So integrate from 0 to t, integrate from. Now here we got to be careful about our variables. So we start at v naught, so that means u starts at mg plus c1 v naught, and that ends at mg plus c1v. Okay, so integrating both sides, we get t equals, that was the hard part, minus m1 over c times the natural log of mg plus c1v over mg plus c1v naught. And again, I think we would certainly like to see this where the v is a function of time, and unfortunately there's no polite way about it. You just got to rearrange. So we can multiply by minus c over m1, and then we can take the antilog of both sides, and so that will give me mg plus c1v over mg plus c1v naught equals e to the minus C1t over m, like so. And then I can go ahead and solve this for v. So let's see, mg plus C1v equals mg plus C1v naught e to the minus C1t over m. So then we can subtract mg. Let's see, we can divide everything through by C1, and then we can subtract mg over C1 from both sides, and that gives me v equals minus mg over C1 plus mg over C1 plus v naught e to the minus C1t over m. All right, let's see if this at least passes our sanity checks before we move on. So again, get in the habit of checking the endpoints. First endpoint you should think about is t equals 0. If t equals 0, that makes the exponential equal to 1. Then that means these terms cancel and I get v equals v naught. Whew. Okay, good. That at least makes sense. We also know now we're not going to hit a speed of 0. We know from before that we're just going to hit some sort of terminal velocity. So let's see if that makes sense. At t equals infinity, this will be e to the minus infinity, which is 0, makes this whole term 0. And I get minus, that's good because it's going down, mg over c1. So that means we can interpret the minus mg over c1 bit, or the mg over c1 bit right there. We'll call that the terminal velocity, although technically I'm writing that as a terminal speed. And also, while we're at it, we can take a look at the exponential. And we've seen decaying exponentials before in our intro classes. We usually write it as some e to the minus t over tau, where tau is our characteristic time. So our characteristic time for the process, tau, is m over c1. So if we put the two of those together, we can rearrange this just a little bit, and you'll end up with v equals minus vt, and that minus is just because we're pointing down. 1 minus e to the minus t over tau plus v naught times e to the minus t over tau. All right, let's look at the two terms individually and see how to think about those. If I look at the rightmost term, at time 0, the exponential is 1 and goes, at time infinity, goes to 0. So effectively, our initial velocity is fading out. And here, this is a excuse me, an asymptotic increase. So we start with 0 for this at time infinity. This approaches 1, and we've got this minus sign here, so just meaning down. So eventually our terminal velocity fades in. Okay. So as an example, if we do the classic intro physics drop a rock kind of thing, we would be looking at falling from rest. That would correspond to our initial velocity being 0. So if our initial velocity is 0, that whole right-hand term goes away, and we get something that looks maybe a little more familiar to us. V equals minus terminal velocity times 1 minus e to the minus t over tau. All right, so remember these decaying exponentials, the magic number is 37%. After one time constant, this is 37%. Two time constants will be 37% of 37%, which is about 14%. Three time constants, 37% of 37% of 37%. That's about, round numbers, about 5%. Now here we're going to be subtracting those magic numbers off of 1. So I could make, if I wanted to, I could make a quick little table of how our velocity, so start with the time here in units of our time constant, and then our current velocity or current speed in terms of the terminal speed. So at time 0, we're at rest, 0%. At one time constant, we'll be at 100% minus 37%, so we'll be at 63% of terminal velocity. Two time constants, that would get us to 86%, and three time constants would get us to 95%. And if we wanted to, we could go from there. But the point I'm trying to get is that after just a few time constants, our deviation from constant speed gets pretty small. And so you can kind of pick where you feel comfortable with that. 3 time constants, 7 time constants is often used as a marker for, constant enough, but somewhere in there. Okay, so that concludes our look at linear velocity dependent forces. The next video will take a look at the quadratic case.